All right, so this video is going to be going over how we write matrices and some matrix notation, and just introducing you to the vocabulary of our course together. So most of your mathematics up to this point, a line has just been y equals mx plus b. A linear equation, as far as our course is concerned, means that all of our x variables here don't have any exponents, so it's just like x to the power of 1, but we're actually going to go past the second dimension, okay, in this class. Not for a little bit, but just kind of hold tight in there. So we're going to call these x1, x2, all the way up to xn, and then in front of those variables, we're going to have coefficients, so numbers, and they're real or complex coefficients, so that's important. And then b is also a coefficient. So what's important here, if you look at this example where it says a system of linear equations, is that all of your x's are to the power of 1, and then everything in front of those is a number, and then they're equal to a number over here. Now, a solution is the list of numbers which makes each equation true. Meaning if I plug the number that we get for S1, S2, all the way up to Sn into each one of these equations, it's going to equal 8 in the top. It's going to equal -7 on this second one. The set of all possible solutions is called the solution set. And we say that two linear systems are equivalent if they have the same solution set. Okay, so two systems, we can have two separate systems. We call those equivalent if they end up having the same solution set. All right, so let's go ahead and do a linear system here in terms of what we would have done maybe in college algebra. And so I want to do this by graphing, elimination, and substitution. Well, if I'm going to use graphing, then I'm going to change this to be x minus 2y equals -1 and -x plus 3y equals 3. Now, when I switch over to Desmos, I don't need to solve these for y. If you had a TI graphing calculator, you would need to solve these for y. But in my Desmos screen, I don't need to do that. I'm just going to plug these in as they are, and let me show you what that looks like. Okay, so I have plugged in x minus 2y equals -1. I have plugged in -x plus 3y equals 3. And you can see that the point in which both of these equations are true is at the point 3, 2. Now I want to make sure we understand this red line, these are all the different x's and y's that are possible. I could plug in -1, 0, and that is true for the red line. I could plug in 5, 3, and that is true for the red line, but it's not true for the blue line. The only point that is true that is on both of those two lines is the point 3, 2. Let's do this by some other methods. Our elimination method is when you have the same number in front of the same variable, but one's positive and one is negative. So essentially I'm going to be adding these two equations with each other, and because I have x1 and a -x1, when I add those two, they cancel out or they become eliminated. So when I go ahead and add the rest of these, I end up getting that -2x2 plus 3x2, so 1x2 must be equal to -1 plus 3, must be equal to 2. Then you actually use what's the substitution method to go back in and solve this for x1. So I'm going to just use this first one. x1 minus 2 times 2 equals -1. x1, when I add 4 to this other side, I get 3. And you can see through this method, I get 3, 2. Another way we could do this with just full substitution method is you could have solved this first equation for x1 by adding 2x2 to this other side. You can then substitute that in. Solve that for x2, plug back in, solve for x1, and go from there. So those are like the three college algebra methods. I also want us to talk about two special methods. And again, I'm going to plug these into Desmos and look at these two graphs so you can see what this looks like. So let's go ahead. X1 is going to be X, X2 is going to be Y. And let's look at this first graph of these parts, this first equation, linear system of equations set. So notice these two graphs are parallel. They never intersect with each other. And the reason is if I were to multiply through by a negative, you would end up getting the same left-hand side, x minus 2y, equals, and then a different right-hand side. So the combinations of x and y on the left-hand side being the same, but equal different like outputs on the right-hand side, that's what's going to cause this. You could also solve both of these for y, and you'd get that they have the same slope, but different y-intercepts. So we say that this has no solution because there is no intersection. There is no one point in which both of these share a solution. All right, let's look at our second one right here. So I'm going to say x minus 2y equals -1 and negative x plus 2y equals 1. Notice when I make that change, there is now no distinguishing characteristic between these two lines. In fact, if you multiplied this by a negative all the way through, they would be the exact same line. Therefore, they are going to have a solution set that is true for every xy of these like shared lines here. So there's infinitely many solutions because there's infinitely many points that these two lines would share with each other because they're the same line. So we can say they're the same linear equation, where here these were parallel lines. All right, I want to go ahead and write these two in what we call matrix form. Now, the coefficient matrix is just going to be the numbers in the front of your variables. So here in example 1, my coefficient matrix would be 1, -2, -1, 2. My augmented matrix includes my B term over here. And you can kind of give a little bit of a space. When I go into solving these, I actually like to draw a line there. That's what my linear algebra teacher taught us to show that this was your coefficient matrix, and then this was your right-hand side, if you will. But that's how we're going to write this system into matrix form. Why don't you go ahead and pause this video at this point, try doing problem number 2, and then we'll unpause and see if you got the right answer. All right, so you should notice that the coefficient matrix is the same for the left-hand side, and then for the right-hand side, it is the augmented matrix with just the right-hand side being different. All right, we're going to talk about just one more example, one more skill. We're going to expand into a third dimension space here. So now we're not really going to worry about calling this like X, Y, and Z. We're just going to leave this as like these are linear equations because all of the X variables don't have any exponential powers. We also have coefficients in front of all of our variables, and they're equal to coefficients that are real and complex numbers on the right-hand side. So a coefficient matrix is actually going to be what we call a 3 by 3, and we're going to talk about size of matrices here. So a coefficient matrix is going to have just the numbers in front of our x1, x2, and x3 inside your matrix square. Now notice in equation 2, I do not have an x1, so I'm going to put a 0. In equation 3, I don't have an x2, so again, I'm going to put a 0. If I wanted to make this an augmented matrix, the only thing I would have to do is add in that side. Now in the textbook, it's not going to have this line here. That's just something that I personally put in there to show like this is my coefficient matrix and my right-hand side of my system of equations, okay? Now the coefficient matrix was a 3 by 3. We do rows by columns. When we talk about the size of a matrix, our augmented matrix is going to be a 3 rows by 4 columns.